All right, so for your response question, actually there's two of them. Okay, but we'll see how far we get. But the way, guys, the way we're gonna do this is I'm gonna go over this with you guys piece by piece and have you guys just solve a little bit at a time. All right, so this is a long for your response question. So they would recommend like 25 minutes for this one. Okay, so normally you guys get like two long ones and two shorter ones that take about half that time. Right, so what do you got here? You can usually get a lot from the diagram. It looks like a cannon is firing a cannonball. Ooh, guys, this is a scenario that you guys have seen over and over for the past couple weeks. So this looks like an explosion type situation, like a collision in reverse. Hey, you know what this reminds me of? You guys remember that Magic School Bus clip? Pitcher throws the ball on a frictionless field and slides back the other way. I think that looks identical to that. That's why I got this one handy ready to go. It's right there. Okay. So if I was sitting in front of the AP exam right now and I saw that diagram, I would think, this is probably a momentum related question just from that diagram. Students launch marbles mass m sub m. So m sub m, mass of a marble, horizontally. Yep, so it shows from a toy cannon with mass m sub c. So m sub c, mass of the cannon. Conveniently, maybe capital M could be a large mass of the cannon, and small m could be the mass of the marble. Okay. Where the mass of the cannon is always greater than the mass of the marble. Okay. Each time a marble is launched, the cannon slides backward before coming to rest. Guys, if the cannon is going to slide and come to rest, that means, what do you know about the surface? Is there friction or is it frictionless? Has to be friction. Because if it was frictionless, wouldn't it just slide forever? Okay. Okay, so there has to be friction. Hey, you know, this kind of reminds me too of when you guys were doing collision carts. I know that was a low friction track, but some of you guys were saying, oh, if the cart like comes to rest, and say, okay, well, now you're considering that there is a little bit of friction on the track for that to happen. We consider that. Okay. All right. So the coefficient of kinetic friction, there you go, between the cannon and the ground is mu. For each launch, the students use a new marble of different mass. Ooh, so they're changing out the mass of the marble. Interesting. So maybe this could be a marble, and then later on, this could be a marble, this could be a marble, this could be a marble. But maybe here's your cannon right here. It's blasting each one of these. Well, they're a marble shape. I guess we have cylindrical shaped marbles in physics. Yay! Welcome to physics. Where there's no, okay. The students record the distance x that the cannon slides backward for each launch. All right, so you guys go with the premise. Question A. This is how we do this. If you guys just write this all in your notes, I'm just gonna give you credit for doing this as long as you're in class. If you're in class, just working step by step. I'll give you guys some points in the grade book. But go ahead and you don't have to turn anything in today. But put this all in your notes. Put it all in your notes. Without manipulating equations, briefly describe what happens to the sliding distance x that the cannon slides backwards as the students increase the mass of the marble. Right, so here, if these are your marbles right here, as you go from the small one to the big one, right, and we got the same cannon over and over and over. Right, right. What's going to happen to the sliding distance x? Go ahead. No, they said without manipulating equations, but maybe you could sort of have some equations in your mind that you could kind of play off, right? Go ahead and write down maybe a couple sentences, a few sentences, right? And then I'll flip to the answers, and we'll check the answer here in a minute. All right, recording's back, resumed. Let's walk around, checking out you guys' answers. Yeah, you guys had some good ideas. Right, so the fact that they said the same speed regardless of the marble size, that's a really nice simplification. I'm just saying this for the recording here. Right. Because you think, well, that would require different explosion energies. Like if it was really the same speed for all these, it'd take more and more energy, right? The more it was blasted, right? So they could have gone either way on that. So they gave you a really nice simplification here. Some of you guys had some good answers in terms of like Newton's third law, because to blast a bigger mass at the same velocity, that would be more energy and more force then, right? But let's see what they have in their answer key. Right. So part A, they got 2 points here. Right. So the first point, earned for using conservation of momentum to indicate that the larger marble means a larger cannon speed, or, right? So guys, if you said anything about conservation of momentum, then that would be a point, or, but there's an alternative they have here. Okay. Or, using a combination of Newton's third law leading to Newton's second law to indicate that a larger marble mass means a larger cannon speed. And yeah, some of the guys I was walking around said something like that. Say, well, it would be a larger blast force, which would be a larger force back on the cannon. There's Newton's third law. and you'd be like F equals ma. Okay, so you could do that. So
where does the second law come into play?
F equals ma, because if it's a larger force acting on the cannon, then it would cause it to accelerate more during the blast, which would send it further. Something like that. Okay. Okay, so there's two ways to get that first point. You can say momentum is talk about forces, right? Either momentum or forces. Okay. And the second point, for explaining why the larger cannon's speed therefore would result in a sliding a greater distance. Okay. So if it's going faster as the recoil speed, then it's going to slide further. Right. There you go. There's the two parts. Right. All right, so you guys go with the first 2 points. So keep track on your paper, of course, how you're doing. Question B, guys ready for question B? Says students find the following equation on the internet to describe the distance x that the cannon slides backward. Here, I'm gonna write it a little bit bigger here because so there's a lot going on in this fraction. So they're saying this: the distance the cannon slides is equal to, it's a fraction. They got the mass of the marble squared times the blast speed squared. Remember that blast speed is constant. That was one of their simplifications. Divided by 2 times the gravity field times the coefficient of friction times the mass of the cannon squared. Right? Right? So that's what they're saying right there. So they found that on the internet where everything is true. Whether or not the equation is correct, right, so maybe this is true, maybe not, right, as if the internet ever lied. Is it consistent with your prediction in part A? Remember, you guys in part A said, well, the larger mass marble, it should cause the cannon to slide further, right? Would this equation be consistent with that? Briefly justify your answer. So go ahead, write down what you think would be a good justification. I'll give you guys a minute there. I'll pause this recording, and then we'll flip to the answer key and check that out. Recording, resume. All right, so guys, I think you're looking at the relationship between these two here, right? Here's the mass of the marble, here's the sliding distance. According to this equation, guys, if you say triple the mass of the marble, if you triple the mass of the marble, what should happen to sliding distance? Should be 9 times the distance, right? Right. So see how do they score part B? Okay, this is also worth 2 points. The response accurately includes both of the following criteria. So they look for both of these. So for, I guess you get both or nothing. 1 point for using functional dependence between mass and sliding distance, mass of the marble and sliding distance x, right? And 1 point earned for a claim that since mass of the marble in the equation increases, x would also increase. Here's an example response. Yes, the equation matches the mass of the marble, matches that as the mass of the marble increases, the slide distance of the cannon also increases. Okay. The mass of the marble in the numerator of the equation. So if the numerator increases, the slide distance will also increase. Right? Like that can take care of that, right? Oh yeah. Yeah, you could say sliding distance is proportional, like directly proportional to the square. You said something about directly proportional to the square of the mass. Yeah, so they're talking about like the numerator, right? Increase the numerator, that increases the overall fraction. Okay.
I got the second point, but what is the first point talking about?
Functional dependence. So they're related in a function to each other, like a function, like sliding distance is a function of mass, right? So, yeah, it kind of all goes together, right? Okay. I think if you get the second point, you should kind of pick up the first point too. They're all kind of same thing. Okay. One changes, the other changes. All right. So, all right. Looks like yeah, I wanted to go through and solve this with you guys. I solved it differently earlier. How do you do this? Oh, okay. Guys, I wanted to check and see, does this actually work? Is it a true equation? Because they found this on the internet. Is it really true? So we're doing a side thought here. I guess AP thought, well, maybe it's a little bit too complex. So yeah, this just kind of popped out my notes from last year, right? But I solved it a different way this year. So okay, let's try this out. Start with this. Say sum of momentum before the explosion equals sum of momentum after the explosion, because this is like a momentum type question, right? Guys, before the explosion, how much momentum was in the system? 0 kilogram meter per second. Okay. And then we have the mass of the cannon times the speed of the cannon one way, plus the mass of the marble times the velocity of the marble, which I'll just call V, going the other way. All right, is that true?
Sure.
Okay. And then if you want to figure out something about the distance the cannon slides to a stop, then I don't see that anywhere in this equation. But that's probably mostly related to which variable? Yeah, the speed of the cannon. So let's solve for that. Can you guys go ahead and solve for that? What is that going to look like? Right. That would look like that, right? Okay. So that's how fast the cannon gets sliding right after the explosion. Now, if you want to solve for how far does the cannon slide, I think now there's two ways to do it. Let's do an energy method, like an energy work method. Right. Can you guys set up an energy equation? Kind of like a car braking to a stop. Right. It'll be an open system. So sum of energy initial minus work done by friction goes to what if the cannon comes to a stop? 0 joules. Yeah. Okay. And what type energy did the cannon have right after the explosion? Kinetic. So there's your 1/2 mass of the cannon, speed of the cannon squared. Okay. Now work done by friction. Guys, what's the formula for friction? Yeah. Okay. So friction force times sliding distance. Okay, and that's actually what we want to find. 0, right? And right, and friction force.
Coefficient friction.
There you go. Coefficient friction times normal force. And guys, what's the normal force equal to? Yeah, the weight of the cannon. So that would be like that, right? I'll substitute right there. Okay. All right. All right. Okay. So here, no, write this a little cleaner. So got 1/2 mass of the cannon, speed of the cannon squared minus coefficient friction times, and then the normal force is equal to the weight of the cannon times sliding distance. We're solving for this is here. Okay. I'm sure. Okay. All right. Now here's from momentum. Here's the speed of the cannon based on well how fast it blasts the marble. Goes right there. You guys can see that in right there.
Yeah.
Okay. Go ahead and finish solving that. Give you guys some algebra practice right there. Go ahead, finish solving that. See what you get. Stay a step ahead of me. You guys getting that? Like that? I think that's what they came up with too, right? So what they came up with? So was that equation from the internet correct? Yeah, I think it's completely correct, isn't it? All right. All right. Let's navigate this bit. So the question that you just answered for points was if you increase the mass of the marble, what happens to sliding distance? Should it increase? And you said, yeah, not only is that true, that's a square relationship. So if you triple the mass of the marble, it should be 9 times the sliding distance from the cannon. Okay. If you did blast the marble faster, the cannon would also slide back further, and that would also be a square relationship. Guys, what if you increase the mass of the cannon? Does the cannon slide back faster or slower? or sorry, further or not as far? Not as far, right? Because that's an inverse type relationship. Right? So if they ask that question, you say, oh, well, that's inverse. The more mass cannon, the less far it slides. Okay. What if you increase the friction? If there's more friction, what happens to sliding distance?
Less far.
Not as far. Yeah. And what if you increase the gravity field of the planet?
Less far.
Yeah, not as far. Ah, because that's also inverse. Do you guys see it? And I think each one of those individually makes sense too, doesn't it? Checks out. Okay. You guys see that? All right. All right. Right here. Okay. Again, here, I'll just flash this up here real fast. I think I did this one last year. Right, so I solved it a little bit different. I think I went through Newton's second law of motion, but got the same answer. Okay. All right. And so if you want to check out that recorded later, you guys can kind of take a look at that. All right. Oh, hold on. Are we on part C? Oh, yeah, part C. Without manipulating or stating equations, briefly describe whether it would take more work. Guys, what's the units for work? Yeah, so 4 times distance, and the unit is written in joules. Yeah, joules. Okay. To stop the marble or stop the cannon after the marble has been launched. Ooh, justify your answer. Is it more work to stop the cannon or more work to stop the marble? Go ahead. Yeah, pause this recording and let you guys write that one down. All right, recording resume. All right, so I did a show hands and it was about a 50-50 split. Half you guys thought more work for the cannon, half you guys thought more work for the marble. Right? So let's see. Now you guys know momentum is mass times velocity. Okay, guys, does the cannon and the marble both have the same momentum? Yeah, opposite directions, but that's like this right here, right? So it's the same amount of momentum, just opposite directions. But if we're talking about how much work does it take to stop, that's an energy concept, right? And guys, what energy equation involves both of these ingredients? Kinetic energy. And what's the formula for kinetic energy? 1/2 mv squared. Ah, right. So here, I'll do a numerical example, and then if you don't see it yet, I think the answer is going to pop out. Okay. So suppose mass of the marble is like 1 kilogram. Just make up silly numbers. And mass of the cannon is like let's say 2 kilograms, like double. Okay. And then they get blasted at some speed. Let's say the speed of the cannon going back could be like 10 meters per second. Okay. And the speed of the marble, or just V, speed of, or no, that'd be VM, something like that. Okay. Guys, what's the momentum I just gave to the cannon? 20 units. Therefore, what's the momentum on the marble? Also 20 units the other way. So what does the speed have to be? 20 meters per second. You guys see if the marble has half the mass, it has to be going twice as fast to conserve momentum. Okay. Maybe it could stop on a negative sign, but you guys get the idea, right? Okay. All right. So let's put these numbers in the kinetic energy equation. Say, what's the kinetic energy of the cannon? What's the kinetic energy of the marble? And we'll compare these things. Because whichever one has the greater kinetic energy, wouldn't that take exactly that much amount of work to stop it? Right. So let's see. If you have half the mass, but twice the speed, therefore, how's that going to work out? So got 1/2 mass of the cannon was 2 kilograms. Speed of the cannon was 10 meters per second. We're going to square that. That's like, is that 100 joules right there? Right. By the way, kind of look for that. If you're running a kinetic energy equation, AP likes to pick 2 kilogram objects because 1/2 and 2 cancel out really nicely. All right. So, right. But the marble has half the mass, but double the speed. But guys, that double speed's getting squared. So in terms of the energy, does it count even more?
Yeah.
Ah, so 20 squared is like 400 divided by 2. That's 200 joules. Ooh. Does the answer just pop out of the page right now? Which one takes more work to stop? The marble. Ah, guess that. Right. Yeah, if you're doing any AP question and you get a bunch of variables, like all right, make up some numbers and play around with it. You know, same thing with the quizzes I give you guys, right? If I ask you guys in terms of variables and you're really stuck, just make up some numbers and play around with it, and yeah, it'll lead to the answer. So it's one way to think about it. Right. So let's see part C, how they score this. Okay, we've got 2 points here. Wait, we're on C, right? Okay. 1 point for a claim that the marble requires more work to stop with an attempted justification. So if you pick the marble and you at least attempted to justify that by itself, they're giving you 1 point. The other point for a valid justification. Here's an example response. The marble requires more work to stop because the marble has greater kinetic energy and thus a greater change in kinetic energy in order to stop. Yeah, right? Okay. All right. All right, you guys good on part C? All right, let's check out D. Here. Students correctly derive the following equation, work done on an object initially at rest, the momentum of an object and the mass of an object. Work equals p squared divided by 2m, momentum squared divided by twice mass. I meant to show you guys this a minute ago. Anyway, do you guys remember this one? It says a little bit more detailed poster, right? So I got the derivation right here. Here's momentum is mass times velocity. Here's kinetic energy, y mv squared. You put it all together. Here's the relationship between kinetic energy and momentum, right? And here's the mass of the object. Right? You could have solved it this way too. The green one is rotational. We'll get to in January. But if you focus on this one, here's the derivation. Here's the solution, right? And that's what they just have right there too. Right. No, they're saying the work to stop it, which would be the kinetic energy it started with. So W equals, and that's what they have. Okay. I guess that one. Okay. So that could be handy to know right there. So they're asking though, is that equation consistent with your answer in part C? Justify your answer. I guess one hint is if you got the last question wrong and now you're looking at this and reevaluating. I mean, if this is probably true, maybe you could go back and fix the other one. But go ahead, take a minute. I'll pause this recording. You guys say why that would be true, and we'll check the answer. All right, recording resume. Let's check out the answer to D. You got 2 points. 1 point for a claim consistent with the answer to part C. A second point for the claim that both the marble and the cannon have equal momentum when the marble is launched, and for recognizing that the marble's smaller mass in the denominator means more work done on it. All right. So what they're saying is the fact that they have the same momentum, so the numerator is the same for both the cannon and the marble. So the numerator is the same. But guys, if you divide by smaller numbers, what happens to the overall fraction? It's bigger, yeah, right. So if you divide by 1,000, that'd be maybe a smaller fraction. If you divide by like 1, then that'd be a bigger fraction. Right. So the fact that the mass of the marble is smaller, right, then that would give you a larger kinetic energy. Okay, so that would be consistent. Yeah. Right. So it said something like that. All right. All right. Part E. Where I lost my spot. C. E. Right. Student 1, student 2. You guys see student 1, student 2 talking to each other? AP likes this type of, I think you guys have seen a few of these before already. Okay. So students discuss the mechanical energy of the marble cannon system during the short time interval in which the marble is accelerated inside the cannon. Right. So during that blast, isn't that like a tiny fraction of a second when the marble's actually being blasted? Okay. So student 1 says, but before I read these, I haven't read these yet. Usually how these work out is that student 1 is mostly correct and student 2 is mostly incorrect, but sometimes they're both correct or sometimes they both make a false statement. So we're ready to build any of those. Like any of these are possible, right?
Thanks.
The cannon is pushing the marble forward and the marble is pushing back with an equal and opposite force. Since the work done by the cannon cancels out the work done by the marble, the mechanical energy of the system is constant. Student 2 says the mechanical energy of the system increases while the marble is being accelerated. The marble gains kinetic energy to the right, and the cannon gains an equal amount of kinetic energy to the left. Right. So, okay. Do you guys see each student, I think, has 2 sentences. So sentence 1, sentence 2, and then sentence 1, sentence 2, and they're both underlined. Okay. So question E. Which underlined phrase or phrases in student 1's statement is correct if either? If neither phrase is correct, write none. Okay. And then here, we'll just do E and F together. Question F, which underlined phrase? Oh, Actually, let's do all four of these, right? E, F, G, H, right? So which phrase could be incorrect? Question G, now look at student 2, which is correct, and then H, which is incorrect. Okay, so which is correct and incorrect for each student? Okay, go ahead and do E, F, G, and H. And I'll pause the recording while you guys do that. Recording resumed. All right, let's go through this piece by piece. All right, so each student made a couple of statements that we're going to evaluate one by one, what's correct or incorrect. So student 1, first statement. The cannon is pushing the marble forward and the marble is pushing back with an equal and opposite force. Show of hands. How many guys say that's correct? Who says correct? Right? Does anybody say incorrect? Nobody says. Everybody says correct. Everybody says correct. Yes. That looks like is that Newton's third law of motion? Newton's third law. I think that looks correct. Okay. But the second part, since the work done by the cannon cancels out with the work done by the marble, the mechanical energy of the system is constant. True or false? Does anybody say true? Does anybody say false? False. Yeah. All right. Look at all those winners right there. Right. Because guys, energy, is energy a vector or a scalar? A scalar. So the direction doesn't matter. If it's going to the right or to the left, you just add it all up. 1/2 mv squared one way, and then 1/2 mv squared for the other object the other way, and it all adds up. Right. Oh, yeah.
It doesn't want us to explain, right?
What do they want you to do? Oh, did they not say explain it? Okay, well, yes, sometimes you have to explain these. So yeah, so if they wanted you to explain it, then you could say something like that. You could say, guys, the energy starts out at 0 joules, right? It's all just sitting at rest, no kinetic, no potential. Right? Guys, where does all the energy come from? Maybe the chemical explosion of power, right? Maybe something like that. Right. So, all right, let's check out student 2. All right, so for student 1, did we say true and then false? Okay, student 2 says the mechanical energy of the system increases while the marble is being accelerated. Is that true? Who says that's true? The mechanical energy is increasing. Anybody think it's true? I think it's true. Yeah, because guys, doesn't everything start at rest as 0 joules? Everything starts at 0 joules, and then when you push on something and get it moving, well, now it has kinetic energy. So it had nothing before, and now has a bunch of kinetic energy.
But if
Yeah.
you push on it, wouldn't the system consist of you two?
Well, the explosion is like pushing, right? Right. The cannon and the marble are pushing against each other, giving each other motion, right? By pushing on each other, right? Okay.
How do we know where to start the system? Like where we start it after it's been blasted, while it's being blasted, or at the end? Because this says while it's accelerating.
Yeah. Well, okay. Well, it's accelerating, right? Right. So, yeah. So start at the beginning of the explosion, and then maybe this process ends at the end of the explosion. So for the marble to move from the back of the cannon barrel to the front of the cannon barrel, right? So a tiny fraction of a second, right? Yeah. So yeah, so the energy is definitely increasing. Right. The second statement, the marble gains kinetic energy to the right. Is that part okay? And the kinetic energy gains, is it an equal amount of kinetic energy to the left? You're right, it is not, because that was the last question before. We said the marble is gaining more kinetic energy than the cannon. Okay. Because both the cannon and the marble have an equal amount of what? Momentum. So it's the same force and the same momentum, but different amounts of kinetic energy. Kind of goes back to this right here. Okay. So it could be same force, same momentum, but different kinetic energies. Of course, all the kinetic energy adds up because kinetic energy, guys, kinetic energy, is that a vector or a scalar? That's a scalar versus momentum is a vector. So momentum you do consider right, left. Energy doesn't matter what the direction is. You just add it all up. Okay. All right, let's check. How do they score this? That was E, F, G, and H. E. Oh, we got student 1 statement is correct that the marble is pushing back with equal and opposite force. So the first statement is correct. F. Where is it? Okay. Student 1 statement is incorrect that work cancels out work, except that all the work cancels and mechanical energy is 0. So that part is incorrect. Okay, the second statement, part G. Student 2's statement is correct that mechanical energy increases. Right, the first statement's correct. And then it's incorrect that the kinetic energies are equal. Okay, so correct. So exactly what we just said. Okay. All right, part IE. Ooh, we're getting a graph. So horizontal velocity is a function of time. You guys see these two dashes right here? Do you guys think that's during the explosion? Probably. I mean, just looking at the graph, I think that would make sense, right? So they both start at rest, and then it looks like the marble and the cannon are moving opposite directions with different velocity, or they pick up different accelerations. Guys, what property of this graph tells you acceleration? The slope. Yeah, right. The marble's accelerating more than the cannon, which I think makes sense because it has less mass, right? So same forces, different masses, different acceleration, right? Right. And then looks like right this dashed line, the marble leaves the cannon barrel and goes at constant velocity. Well, maybe constant horizontal velocity, right? Right. And the cannon, hey guys, what's the cannon doing? Is it speeding up or slowing down? Slowing down, right? After the marble leaves it, right? Oh, okay, but that makes sense too because there was some friction going on. Graph shows horizontal component of velocity of the marble and the cannon relative to the ground. Before time 1, the system was at rest. At time 1, the marble begins accelerating the cannon. At time 2, the marble leaves the cannon. Question I. Provide 3 pieces of evidence that together explain why the magnitude of the rate change of the cannon's velocity. Pause right there. That's a really fancy way of saying what? Acceleration. The rate change of velocity is acceleration. That's right. Is less than that of the marble. Okay. Okay. So here, since we just got 2 minutes, I'm just gonna show you guys the answer on this one. So this is question I, right? And so here's what they're looking for. 1 point for recognizing that the same force is exerted on both, right? Like even if you guys, a lot of these AP questions, even if you weren't sure you could get fully to the answer, if you just write statements that are correct, you could pick up a point here or there. I mean, that's just Newton's third law. If you just write Newton's third law, boom, that's a point. Right? Same force on both. Second point for indicating that the larger mass of the cannon results in a smaller acceleration. That's Newton's second law. So we got Newton's third law, Newton's second law. And then third point for indicating that the force of friction acting opposite of the cannon's direction of motion will further reduce the acceleration of the cannon. Oh, yeah. So there could be actually 2 reasons why the cannon accelerates less than the marble, right? One is that it has more mass, but I almost forgot this too, right? There is friction while it's sliding too. Don't forget that too. So if you also include that. Example response, even though the force on the cannon and the marble is the same due to Newton's third law, cannon's acceleration is smaller. So its velocity increases less than that marble because the mass is larger. It's Newton's second law. The cannon also has a friction force opposing its motion, which further decreases the net force and therefore the acceleration. So there you go. All right, so you guys good there? All right, bell's gonna ring in about 20 seconds here. So you guys have a good weekend. You guys remember what's due by the time you come to class on Monday? AP classroom. Oh yeah, good time.